In part 2, I'm going to discuss geometric evaluation and properties of G-transform, characterization of LTI system, and block diagram representation of LTI system. First, geometric evaluation. We did something similar for Laplace transform earlier. For a given impulse response whose G-transform is like this, with the region of convergence, we get Fourier transform of this one. If we take the magnitude and phase, we get the magnitude and phase characteristics of that system. But we can do it directly from pole zero diagram using geometric analysis. There we have a pole at G0, which is A. I mean, pole is there. And if we consider this one, we may rewrite it as by multiplying e to the j omega, e to the j omega. We have a pole at 0, and this one means this. Minus a means this one is a, so minus a means this one. So this one, the other one gives you this, which is denominator. Numerator's value is 1 all the time. So if we take the amplitude of this one and take its inverse value, then that's the magnitude. And we move this point from 0 to pi and then to pi. And we check how the magnitude changes. Then you get the magnitude characteristics from 0 to pi. For example, in this case, pole is close to the point omega is 0. So, inverse of that one is somewhat large. But as it moves away from the origin, the distance becomes larger, which means the magnitude is smaller. So we get a curve like that. In the case of a phase, we get something similar. This phase starting from 0 and increases. And because it is on the denominator, the value is decreasing like this. The same thing applied for the second order system. For example, if we are given an impulse response whose G-transform will turn out to be like this, you can try it, and Fourier transform like that. We see there are two poles. The zeros are on the unit circle, and poles we have 2. And the distance of this one and that one determines the magnitude characteristics like this. For example, in this case, what you observe is that starting at the origin, you have this magnitude, and then magnitude increases as you increase omega 0. And it peaks at some frequency, which I say is that omega value, because this distance is the smallest. Its inverse value becomes the largest. So it draws a magnitude curve like that. You can repeat something similar for phase curve too. Okay, the properties of G-transform. It is similar to the Laplace transform and also similar to Fourier transform and Fourier series. We have properties on the left, linearity, time shifting, scaling in G domain, time reversal, time expansion by RK, g to the k's power, conjugation, convolution, integration, first difference, accumulation, differentiation in time domain. This one, multiplication by n in time domain. I have one example on this. And also, initial value theorem holds for G-transform, which I'm going to discuss in an example. Okay, this example, we consider a G-transform in that form, and we take advantage of the relation we just saw, this relation. If we consider that one, this one turns out to be that. And we know this one. We have that in time domain. And this one means a delay in time domain. And all these are about n times xn. So xn itself is obtained by dividing the result by n. Okay? The next, initial value theorem. We can determine the initial value in time domain directly from the G-transform xg by taking the limitation g going to infinity. Given that G-transform, we can determine the initial value from this relation to be 1. Next, basic G-transforms, which you must be familiar with. 1 minus 1 over g. And this one going to the other direction. This one going to the other direction. And this one n times. And going to the other direction. Cosine function, sine function, and delta function with a delay. Now we consider the causality and stability of an LTI system. This is the case of a causal system having all zero values for n less than 0. For a discrete LTI system, we can say it is causal if and only if the region of convergence of a system function is exterior of a circle including infinity. That means because there is no term for n less than 0, this one happens. We already discussed about this. So if we have many poles anywhere with a region of convergence appearing outside the outermost pole, including infinity, causal system has that property, and if that property holds, it is a causal system. Discrete LTI system with rational representation is causal if ROC is the exterior of a circle outside the outermost pole. Outside the outermost pole. And with HG expressed as a ratio of polynomials, the order of numerator cannot be greater than the order of denominator. We are putting this one as a ratio of NG and DG. Then this one, this ratio, cannot be greater than the order of this one. So that ratio, what does it mean? If the order of this one is higher than that one, what it means is that it can include a term, G. And that means there is a pole at infinity. So it cannot, region of convergence cannot include infinity. That's why we have that term. Without knowing region of convergence, we cannot state the causality of a system. Yeah, because the region of convergence should include that exterior and including infinity. So without knowing region of convergence, we cannot say about causality. Now, stability. An LTI system is stable if and only if the region of convergence of the system includes unit circle. Going one step further, causal LTI system is stable if and only if all the poles of Hg lie inside the unit circle. If all the poles lie inside the unit circle. If it is causal, region of convergence will be outside of the outermost poles. And if it is stable, H1 is absolutely summable. That means Fourier transform converges. If the region of convergence includes the unit circle, that means G transform convergence on the unit circle. That means it is stable. So we made a very important statement saying that stable system should include unit circle inside its region of convergence. Stability condition, we have this well-known G transform with A less than 1 and right-sided sequence, then this one is stable because the pole is inside the unit circle. Likewise, second-order system with the two poles whose magnitude less than 1, that system is stable too because unit circle is included in the region of convergence. Example, causality and stability. Suppose we are given this second-order system with the two poles located at half 2 and two zeros located at the origin and 5/4 at the origin and 5/4. The zeros does not contribute much. Poles are important. If we put it in partial fraction representation, we get this. And we try inverse transform on those, which depends on the region of convergence. If the region of convergence is larger than 2 outer, that means it is right-sided. So we have two terms, both of which are right-sided. So in that case, the right outside means the other one. So it is causal, but it does not include unit circle, so it is not stable. Second case, if the region of convergence is a ring like that, ring like that, it includes unit circle. And one is right-sided, another one is left-sided. And the unit circle is inside the region of convergence. So it is stable, but it is not causal because infinity is not included. Third one, when region of convergence is inward, then both terms are left-sided, and region of convergence does not include unit circle. It does not include infinity, so it's non-causal, non-stable. Okay? Next, we consider characterization of LTI system. LTI system with constant coefficient will take such expression. For example, in first order case, that kind of representation, by taking G transform, we can easily get this. So by determining YG over XG, we get this system function. And by taking its inverse transform, we get impulse response. In general, given an nth order difference equation like this, we take its G transform like that or that, and we determine the ratio, then we get G transform of the system. It has numerator part and denominator part. We can draw the magnitude characteristic out of the pole zero diagram determined by those numerators and denominators. Okay, we consider now the block diagram representation of LTI systems. Given such system function, which may be written in time domain like this, we have seen this one from the beginning of the course. We know that we have delay, multiplier, and adder there. And if we recall the Mason's rule, which I mentioned in part 1, in previous chapter, you get, which roughly speaking is like this, or you may see it right there. Say, roughly speaking, path product goes up, 1 minus loop product. So 1 minus minus, so plus H1, H2. This one has a feedback structure inside. Some examples. Suppose we are given this first order. We may split it into two terms, product of two terms. This one is what we have just seen, and we have that much added. So the second part is for that. We know that the first part makes that kind of feedback structure, and with this input and that output, we have that relation, which is very simple. This one is, if we put it down in time domain, this is this one minus 2 times its delayed value. So we have that. You may question, how come we see 2 delays for first order system? But for that question, I can say that this point is the same point as that one, because this is a delayed variable of that variable, and this is a delayed variable of that variable, the same. So we may redraw it using just one delay. So first order system having one delay. if you apply Mason's rule, you may say that this is a loop, so in denominator you have this. And numerator, you have two paths. One is going this way, the other way going that way. This is 1, this is minus 2 G inverse. Okay? We have this one there, and we have another one cascaded. So this one is appearing there, something similar appearing in front in cascade. That's one implementation. Or we may implement it in this way. And from that we can write down that time domain expression, which says yn is xn minus this one minus that one. So from this drawing, this block diagram, you can check that. Say this yn is xn minus this minus that. The first term is a quarter of yn minus 1. And with minus sign, you get plus on the left-hand side. And one more thing down there. So, second order system having 2 delays. Or you can put it in a partial fraction expansion, getting this, and this one in parallel with that one down there. So there are different types of block diagram representation for a given G transform or system function of an LTI system. As a final example, you consider that. You just saw this on the previous page, and we have some more up there. So 2 terms in cascade. We know this one has this form. We already saw that. And this one is summation of 3 terms. If this one is Vn, and if you determine Yn from Vn, you have just that relation. Say Vn term and Vn delayed. One delayed term and delayed twice. Okay, that's what we get. And some of you may question why we have 4 delays on the second order system. As I mentioned on previous page, these are the same point. So we may simplify it like this. Okay? If you would like to apply Mason's rule, then we have 2 loops. So, first loop product, second loop product. We have 3 paths, 1, 2, and 3. The first, second, third. That's what you get. Okay? Okay, with that said, I conclude part 2.